Hey, let's start the webinar now. Good morning, good afternoon, and good evening. Welcome and thanks to join to WhaleTeq webinar. Today's topic is from theory to practice, a comprehensive guide to conducting accurate tests for ECG, PPG, PWTT, and the respiration rate. I'm Richard Dean. WhaleTeq Technical Support Manager. And I'm honored to introduce today's course. The course contains 30 minutes ECG test method according to international standards, heart rate and SpO2 testing using PPG technology, and the PWTT testing using ECG and PPG signals. And another 20 minutes, I will introduce the respiration rate measurement using impedance and modulation test methods, and the introduction of WhaleTeq's test equipment, SECG 5.0 AIO. And the last 10 minutes, I will give a short conclusions and a Q&A session. Okay, before the introduction, Zoom meeting has a Q&A button here. You can click the Q&A button to type your question. I'll answer the questions at the last Q&A session. And due to the limited Q&A time, unanswered questions will be compiled and responded to in a PDF file after the webinar. Okay. The first topic is the ECG method according to international standard. This slide, I'll take a short introduction of 3 ECG standards for 3 types ECG. Okay, the first type of ECG is a diagnostic ECG. The standard is IEC 60601-2-25, 2011 years version. Okay, this is for a device intends to obtain, record, and display a set of conventional or orthogonal ECG signatures, and provide a diagnostic ECG report. The test include performance and the database testing. Okay, the second one is the ECG inpatient monitor. This standard is IEC 60601-2-27, 2011 years version. This is for a monitor that obtains heart rate and the waveform by ECG. It's used to display the heart rate and heart rate waveform of the monitor patient, as well as an alarm for arrhythmia. Tests include performance testing only. Okay, the third one is the ambulatory ECG. The standard is IEC 6601-2-47, 2012 years version. This is for a system. It's capable of continuous recording and analysis, or continuous analysis and the partial or limited recording of an ECG, which records and stores the ECG and then analyze it in a standalone unit, or records and analyze simultaneously. The tests include the performance and the database testing. Okay, and this slide, I take 2-47 standard performance test as an example. So you can see here, this is the 2-47 performance test, all 12 items here. Okay. Test the ambulatory ECG. This is performance test. In fact, it is an electrical performance test. Okay, all include the electrical signal here. Okay, there are 5 major performances for all ECG standards. Okay, include the -2, -25, and the 27. Okay, 5 major performance. That's amplitude related. So here you can see 101 test item, linearity dynamic range is for amplitude accuracy testing. Okay, the second one is input impedance. All standards with input impedance test here. Okay, the third one is noise related. Okay, noise related in common has common mode, the rejection ratio test, and the system noise. System noise means the internal system noise. Okay, and the fourth one is frequency response related. So frequency response related include low cutoff frequency response or high pass filter, and the high cutoff frequency response for low pass filter, and pass band response. Okay, this is the fourth major test item. And the fifth is the patient pulse related. Okay, so the patient pulse related is in general there are 2 kinds of patient pulse. One is the patient pulse cannot cannot interfere the ECG signal. The second one is the patient pulse must display on the screen, on the ECG screen. Okay, so this is about the electrical performance test. Okay, then I'll take 2 examples of the test item here. First one is the linearity dynamic range. Previous just said this is amplitude related. So you can see the test circuit is like this one. Okay, this is a general test circuit. That means all test items must use this test circuit except the CMR and the system noise. Okay, so except the noise testing, all the tests must use this test circuit here. Okay, so this test circuit with a signal generator here, and the generated signal will go through a power divider, 1,000 times power divider. So this is a 100 kilo ohm, and this is 100 ohm. So if you generate a 1 volt signal, 1 volt PP signal to here, and the VI, in fact, the VI is a 1 millivolt PP signal. Okay, this signal go to P1, and the DUT electrode, one of the electrode connect to P1. So this is a electrode on the test. So the signal positive terminal connect to the P1 to the electrode on the test, and the negative terminal connect to other electrodes. Okay, so this connection means a differential input connection. So the P1 compared with P2 is the, for example, if you generate 1 millivolt, so P1 compared to P2 is 1 millivolt input. Okay, and for the RL, right leg or neutral electrode must connect to P6, and the P6 goes through a 151 kilo ohm parallel with 47 nanofarad circuit and connect to P3, and then connect to P2. Okay, so this is a general test circuit. And here is a plus minus 300 millivolt DC can superimpose on the electrode on the test, controlled by the switch, by this switch. Okay, so for the linearity dynamic range test, you can see the test purpose. Here is a digital ECG, because in the standard, there are two kinds of ECG. One is analog ECG, the other one is digital ECG. So this is a digital ECG. And the digital ambulatory recorder should be capable of responding to and displaying an input signal of 10 millivolt peak to valley. Okay, that means the linearity range, maximum linearity range is 10 millivolt PP, PV or PP. Okay, and in the presence of a DC offset voltage of plus minus 300 millivolt. Okay, so superimpose on 300 millivolt DC, still output still must in the accuracy range. Okay, so test method use a 6.25 Hertz triangular wave, and with 0.5 millivolt, 1 millivolt, 2 millivolt, and 10 millivolt. Okay, so for different kind of amplitude to do the test. And then superimpose and offset voltage plus 300 millivolt and the minus 300 millivolt. Okay, alternatively, you can use a 4 Hertz sine wave here. Okay, then the test result. Okay, the output signal amplitude referred to input should not change by more than 10% or 50 microvolt, whichever is greater. Okay, in this case, just 10%. Okay, because of 0.5 millivolt is 500 microvolt. The 10% is 50 microvolt, so it's the same. So scale the 10% here. So that means the standard ask in the linearity range, the amplitude accuracy is in 10%. Okay. So the tester can like this one. Okay. So this is the simulator, the tester, ECG tester. Okay. We can set up the triangular signal 6.25 Hertz and all different amplitude, 0.5, 1 to 10. Okay. And superimpose on the 300 millivolt and the minus 300 millivolt. Okay, so you can see this is a test table here, right? 4 different kind of amplitude and with DC offset here. So you can see total is 12 items you must test one by one. Okay, for example here, 0.5 millivolt with 0 millivolt DC offset. The test result is 0.5 millivolt. Test result must from the ECG display screen. Okay, so display the waveform amplitude will fill in here. Okay, if, for example, this one, 1 millivolt, if the result is 1.2 millivolt, that means 20% different. So this is a failed test with a red character. Okay, so this one is for use the ECG simulator or ECG tester to test the linearity and dynamic range item. Okay. The second example here is the input impedance testing. Okay, for input impedance testing, the general test circuit will aid 620 kilo ohm parallel with 4.7 nanofarad circuit here, and controlled by the switch, by the S1 here, the switch. Okay, so when the S1 clocks, that means bypass the parallel circuit here. So the signal will go through directly to P1. And when the switch S1 open, that means the signal will go through this parallel circuit to P1. Okay, so the test use 10 Hertz sine wave by millivolt to do the test. Okay, and the purpose, input impedance should be greater than 10 mega ohm. Okay, with DC offset still must greater than 10 mega ohm. how to get 10 mega ohm, I'll calculate later for you. So for 10 Hertz sine wave 5 millivolt signal, the first test will go through S1. When S1 crossed, okay, then here the P1 will measure a 5 millivolt 10 Hertz signal. So you got the amplitude, right? With, for example, it's a reference amplitude. And then open the switch and measure. Because the signal go to 620 kilo ohm, this is become a power divider between the 620 kilo ohm and the input impedance here. Okay, so maybe you can see here, right? This is the DUT first stage amplifier here. So the amplifier plus and the minus terminal with input impedance Ri here. Okay, so signal go to here. So the first time without the parallel circuit, and you can get a V1 result. So here you can see this is without 620 kilo ohm parallel circuit, get V1. And then open the switch, right? Open the S1, and you add on 620 kilo ohm. Okay, then like this one. So this impedance will, with the input impedance, will get a power divider here. So the V2 equals the power divider formula here. Okay, so V1 is the first major readout. V2 is the second major readout. Okay, so V1 and the V2 is already known value, and the R is 620 kilo ohm. So the Ri can calculate by this formula. Okay, the standard ask, steady state output amplitude should not decrease by more than 6%. Or why 6%? So you can calculate it here. If V2 decreased 6%, then V1. That means V2 equals 0.94 V1. So in this result into the formula here, you can get I equals approximate 16R. So it's 10 mega ohm. R is 620 kilo ohm. So this is just for easy calculate 620 kilo ohm. Okay, 16 multiple 620 kilo ohm. So you can get 10 mega ohm here. Okay, this is for the dash 2 dash 47. For dash 2 dash 25 and 27, the result is 20% decrease. You cannot exceed 20% decrease. That means the input impedance must larger than 2.5 mega ohm, not 10 mega ohm. Okay, so this is a second example for the input impedance. So there are many other test items. I just take 2 examples here. Okay, so for simulator, you can see we set up the sine wave 10 Hertz 5 millivolt and 300 and minus 300 millivolt. And then this one is controlled 620 kilo ohm parallel circuit on and off. Okay, and here you can see the table here, right? It's a 0 millivolt. Sorry, it's a reference. Okay, this is 620, no 620 kilo ohm. This is 620 ohm. This is with 300 millivolt, minus 300 volt. So you can get 4 different kind of result. Okay. Then we'll go to second topic. Second topic is the heart rate and the SpO2 testing using PPG technology. Okay, so here PPG means photoplethysmography. Okay, this means using photo to detect the target volume change. Okay, so here is DUT here is a green light DUT. Okay, so the DUT sensor part, in fact, the sensor part is the optical module here. So you can see the optical module include one green LED and one PD. Okay, PD is a photodiode, can detect the light and convert to electrical signal. So the electrical signal can display on the screen, okay, or calculate by the algorithm. Okay, so the green light will emit the green light to the, for example, this is a target. The target is a wrist in a static state. Okay, wrist in a static state. So the wrist include the skin tissue. The skin tissue include epidermis, dermis, hypodermis, and the vein and the artery. Okay, so when the green light emit to the skin, the partially absorbed by the skin tissue, artery, and the veins, right? And the partially reflected back to the PD of the sensor. Okay, so in static state, the volume does not change with each heartbeat, and the intensity of absorbed light and the reflected light is stable. Okay, it is converted into the direct current, the DC, by the PD. Okay, so except the artery, all other skin tissue and the vein is stable. So the green light emit to the skin tissue, partially absorbed by the skin tissue, and the reflect to the PD. Because the intensity is stable, so the DC convert to electrical. The electrical is like this one. It's a DC voltage. Okay, that's why we define it. It is a DC. Okay, for the artery, right? The artery, the blood volume changes with each heartbeat, right? The artery. So, so it is converted into an alternating current, AC, through PD. So you can see the artery reflect the AC light. So the PD detect the AC light become electrical. So this is like this one is an AC signal. In fact, AC signal frequency is the heart rate, right? Because the artery volume change by the heartbeat. Okay, so the darker skin will absorb more incident light. So the reflected light will be weaker, and vice versa. So the DC level represents the skin color range. Okay, and the more elastic artery is, larger amplitude change the reflected AC signal has. So the AC level represents the artery elastic range. Okay, so this is the PPG basic for the green light here. And for red and the infrared device, this is for SpO2 measurement. Use two light, red and the infrared. Okay, so here you can see there are two types, PPG oximeter. Okay, this is a pulse oximeter. Okay, the pulse oximeter determines SpO2 value by illuminating vascular tissue with rapid switching between red and IR light. Okay, that means the red and IR emit the light to the skin. For transmittance, the light will transmit to the other side of the finger, right? And the PD at this side to detect the change, the red and the infrared change. In fact, same as the green light, the change include DC and the AC because the artery change, right? The difference with the red, with the green light is the green light just detect the volume change, but the red and the infrared is different. Okay, so the red and the IRAC signal are sensitive to change in SpO2 value because red and IR light have different absorption rate of O2 HB. O2 HB means oxyhemoglobin. Okay, and the HAV means deoxyhemoglobin. Okay, so when the hemoglobin with oxygen and the deoxygen, that means the red and the infrared will have a different absorption rate. So output, except the volume change, have with another hemoglobin oxygen change. Okay, so the AC and the DC level is different with the green light here. But both a red and the infrared with a different AC and the DC level here. Reflectance type is the same, okay, with different red and the infrared, DC and the AC. So use this AC, DC level, we can get an R value. So R value defined by this one, the red AC divided by DC and the infrared AC divided by DC. Okay, so this 4 value is detected by the PD. So it's a known value. So we can get the R value. And putting this R value into the R curve here. This is a R curve. K1, K2 is a constant. So the R curve can calculate the SpO2 value. So use the red and the infrared LED and PD can calculate the SpO2 value. Okay. So how to do the test here? You can see there are 3 kinds of different test block diagram here. So this is a variable DUT, right? Variable DUT, and for transmittance, this is the variable DUT. Okay, is a clip to the finger. So this is a simulate finger. Okay, so green light, for green light, you can see DUT emit the green light to PD. Okay, the most importance for the simulator to simulate the reflect light is we must synchronize with the green LED. Okay, so green LED emit light to PD. PD detect the light and synchronize with the PPG module green LED and emit light to the PD. So it's almost at the same time to simulate the reflect light. The reflect light different with the real skin is we can adjust the LED 3 parameters. Okay, the first parameter is the BPM, okay, bit per minute. That means the AC frequency. Okay, AC signal frequency. Okay, the second one, we can adjust the LED light intensity. So that's a DC level. So the DC level higher, that means the LED emit higher intensity LED, the light to PD. And the same, the AC signal amplitude. So AC signal amplitude means the artery elastic range, right? The DC means the skin color range. Okay, so we can use this way to simulate the different kind of people, the heart rate. Okay, for the SpO2 measurement, use red and the infrared LED. So the same, we have 2 PD. One detect red, the other one detect infrared, and synchronize with the DUT LED to emit red and the infrared light to the UTPD. Okay, so same, both infrared and the red LED can adjust the 3 parameters: BPN, DC, and AC. Okay, and for the transmittance, it's the same. It's the same idea, but because of the transmittance, the LED and the PD at a different side. It's not at the same size here, right? The same side, but this is a different side. So the simulator must simulate the finger, okay, the finger. So the finger here, the upside, if the UT upside is LED, then the simulator finger must PD here. Okay, another one is here. It's the same. When LED emit red and infrared light, the PD will synchronize with the DUT LED and they emit the different LED light to the DUT PD here. Okay, so use this way, we can do some measurement function to simulate the skin reflect light or transmit light. Okay, so this is for the heart rate and the SpO2 measurement idea here. Okay, the third is the PWTT. In fact, PWTT testing is just because the simulator can simulate the ECG signal and the PPG signal in the same machine. So we can adjust the delay between the ECG peak and the PPG peak or PPG foot. Okay, PPG, if we measure PPG here is a PPG peak, that means PTTP. Okay, PTBP is PTT peak. Okay, PWTT means post-wave transit time. Okay, so post-wave transit time peak delay with the ECG peak here. So it's a PWTT delay. Okay, and the PTTF, F means foot. So this is this point delay with the ECG peak. So if the simulator can generate these two signals with time difference, then we can do the PWTT test. And the PWTT currently the application is for estimated continuous blood pressure value measurement. Okay, so this is for PWTT test here. Okay, the next one is for the respiratory measurement using impedance and the modulation test measure. Okay, so respiration rate measurements, there are two methods. One is the impedance test measure. The other one is the modulation test measure. Okay, so impedance test measure use a special circuit to do the test. Okay, the respiration rate RR is defined as the measurement of a person's breathing rate per minute. So it is BRPM at rest. Okay, when the thoracic cavity expands or reduces, right, or inspiration or expiration, chest impedance increase or decrease. So if we can simulate the chest impedance difference, then we can get the respiration rate. Okay, so using ECG lead, for example, lead 1, lead 2, lead 3, can measure the transthoracic impedance change through a fixed current high frequency signal source generated from ECG internal respiration circuit. So here, so this is the ECG internal fixed current high frequency generator and the receiver. Okay, so this signal is a high frequency fixed current and generated to lead. For example, here the RA, right, 2 electron. So this is a lead one, and this signal go to test equipment. In fact, for the real person, this signal will go to the chest, right? The chest impedance change, then the feedback, the fixed current feedback voltage change. Okay, so the display can get the voltage change in waveform here. The waveform frequency is the respiration rate. Okay, so for the test equipment must have a circuit. The circuit can change the baseline impedance and the time varying impedance. Okay, baseline impedance means the chest baseline impedance. Time varying means when breathing, the chest volume change, right? That means the chest impedance change. Okay, so test equipment uses baseline and time varying impedance circuit to simulate the transthoracic impedance change. Okay, so use this way and can get the breath waveform here, and the ECG receiver circuit can calculate the respiration rate. Okay, another one is the ECG. Okay, ECG means impedance cardiography. Okay, it's another application, not for respiration, it's for ECG. The ECG uses the same idea to change the impedance, okay, to measure the ECG. But the impedance is different range, okay, compared with the respiration rate with different range. So if the baseline and the time varying impedance circuit can change the range, then can do the ECG measurement. Okay. Okay, the second way is the modulation test method. Okay, so method extracting respiration signal where ECG technology is called EDR. Okay, this is an ECG derived respiration, and via PPG technology is called PDR, PPG derived respiration. Okay, there are two modulation methods, EDR and PDR. Okay, there are three types of EDR analysis to detect changes in the respiration rate. So when breathing, the heart exit deviate and cause the ECG amplitude to change. So when breathing, the ECG amplitude will change. So this is amplitude modulation. That means the signal modulate, the breath signal modulate the ECG amplitude. Okay, so like this one. So the ECG peak amplitude change modulated by the respiration, by the breathing. Okay, and the second one is the heart beating rate change. When breathing, the heart beating rate change. Okay, so this will change the frequency, the peak frequency. So you can see longer, shorter, the change. Okay, the frequency change. So this is the frequency modulation method. And the third is the ribs and the diaphragm position change. Okay, this leads electromyography EMG change. Okay, so this change will change the ECG baseline. So like this one, the baseline change. Okay, so this is a baseline modulation. So there are three types of EDR. Can measure the breathing rate or respiration rate. Okay. The second method is the PDR, right? PDR, same. There are three types of PDR. So when breathing, the heart volume change, right? The heart volume total heart volume change. Okay, this will cause the PPG amplitude change. So the same, the amplitude modulation. Okay, like this one. Okay, this is the PPG signal, not the ECG signal. So the PPG peak amplitude will change. Okay, so this is because of the heart volume change. Okay, same sequence is the same, the heart beating rate change. So this is a frequency modulation, right? The heart beating rate change, so it's frequency modulation. And the third is the thoracic pressure cost change in blood flow. Okay, when blood flow, the thoracic pressure change. So this will affect the baseline of the PPG. Okay, so you can see this is the baseline change. So it's just very similar with the EDR. There are three same modulation change: amplitude modulation, frequency modulation, and baseline modulation. Okay, so use this PPG waveform and the ECG waveform. The DUT can measure the respiration rate. Okay. Okay, so this is for respiration rate measurement, and then I'll introduce the test equipment. Okay, WhaleTeq test equipment. We have one model is SECG 5.0 AIO. Okay, so it's like this one. Okay, the front panel is a touch screen tablet. Okay, so you can touch to select the parameters or use mouse to select parameters. And the side panel here, you can see this is the ECG electrode, include the RA, LA, RL, and the V1 to V6 electrode. Okay, and the rear panel we have because this is include a tablet, so we have some USB interface, right? And one 15-pin types connector. This connector is a special connector for the PPG module. So this one is an example for transmittance PPG module. Okay, and some output, because just say the ECG general test circuit has a 1,000 time divider. So before attenuator is a 1,000 times bigger original signal, so it can go out from here. Then if here connect to the oscilloscope, you can use oscilloscope to monitor the output signal. Okay, so this is the SECG 5.0. So this because we have a ECG circuit inside and with the all electrodes output, so we can do the ECG performance test. Okay, this is built-in circuit predefined the ECG standard. Okay, and the standard system. Okay, and the second one, we can measure the heart rate and the SpO2 testing. Use the reflectance or transmittance PPG module. Okay, and the third, we can simulate the PWTT signal. Okay, for device with PWTT function and the test, because we already have a ECG and the PPG signal. And fourth, we have a respiration rate measurement. Okay, so this is for impedance type and the wave modulation type to do the respiration rate test. And we have auto sequence function we can set different setup, then play the different setup one by one. So this is auto sequence, and then we can play raw data. So any recorded raw data, we can replay. And we have a SDK function. So the software development key. So all the machine can control by another PC use C# language or Python English language. Okay. Okay. So the major function in the front panel here, you can see we can generate a different kind of standard signal to do the test. Right. We have a spatial add-on. This is the respiration rate add-on. And we have a ECG spatial function. Spatial function, we can generate some ECG standard waveform, right? The pre-roll data, and we can add some noise, NST noise, to the raw data signal, our standard signal. Okay, we have auto pacing, heart rate, frequency scan function, and then we have a lead-off test function. Lead-off, well, we have a 10 mega ohm, 20 mega ohm, and open the electron on the test. Okay, and the auto sequence. Here, the standard assistant. Standard assistant means we hit the 25, 27, and the 47 test procedure in this software. So, for example, we just see at the beginning the linearity dynamic range. We have table, right? The table you can fill in all the table, then do the automatic test. So this is a standard assistant. Okay, and then we have a SPO2 and the PWTT test. Okay, so all function in the front panel here. And the respiration rate, you can see here. This is the respiration rate, and this is the impedance. This is the modulation test. So respiration rate, we can set up the rate here, the BRPM, right? And the apnea time, yeah, we can simulate some pulse breathing, okay? And the inhale and the exhale ratio. And then for the impedance, the baseline impedance and the variation impedance. Okay, so the maximum variation is 5 ohm, plus minus 5 ohm. Okay, for baseline here, for the modulation here, you can see the baseline modulation, amplitude modulation, and the frequency modulation. The maximum variation we can set up to 16% modulation. Okay, and for respiration rate test, I just said the ECG test with a different impedance range compared with the respiration rate. So you can see the respiration is set up from 0 to 170 BRPM in 1 BRPM step, right? Tonight with 100 ohm, 200, 500 to 4,500 in 500 step. And the impedance variation 0 to 5 ohm in 0.05 ohm, right? And the 5 to 10 ohm in 0.1 ohm step. But the ECG test is different. You can see you can set up 20 to 100 ohm in 20 ohm step, and 0 to 1 ohm in 0.05 ohm step, and 1 to 5 in 0.1 ohm step. Okay, this is for the ECG test. Okay, both impedance measurement, we can use this impedance variation range here. Okay, so next one is the PWTT, right? We can set up the delay between the ECG peak and the PW peak or PW foot. Okay, and I will give a little conclusion here. So there are 3 ECG standards for 3 kinds of ECG performance and the database test. 5 major performance for all ECG standards. That's amplitude-related input impedance, noise-related, frequency response related, and the pacing pulse related. And the PPG technology is currently applied mainly to heart rate and SpO2 measurement. Three major parameters, BPM as heart rate, AC level represent the artery's elastic range, and the DC level represents the skin color range. The PWTT can be adjusted to effectively verify the accuracy of the blood pressure measurement algorithm. Okay. RR and ICG. ICG is impedance cardiography, major chest skin impedance change. Get BRPN and the CO. CO means cardiac output. Okay. The equipment simulates the impedance change with the baseline and the time varying impedance circuits. Okay, SECG 5.0 AIO can support ECG, PPG, PWTT, respiratory, and ICG applications. Okay, so I finished the presentation here. Have any question? Impedance test miss for respiration rate. Can impedance test method for respiration rate be used for biopsy and the EDA application simulation testing duty? Yeah, I think the biopsy, the ICG test is for biopsy simulation. Yeah, because we currently study two kinds of application. One is the ECG respiration rate test. So we got the range here, and another one is for ICG test range here. So maybe there are some other different kind of range. You can contact as our salesperson, then we can, because all this we develop by ourselves. I think our RD team would like to create some new application for the biopsy. Okay. Okay. Any other question? So I think here from Brazil have a customer, Campero, Mr. Campero. Do you make people technical training to use your equipment? Okay. Yes, of course. We offer the operation training if you purchase our product. And if you want to do the standard test training, you can contact our sales people to get charge the training for different kind of standard, maybe stage 2, stage 25, 27, or 47. Yes, we offer all this training. Okay, another question is from Thailand. Sorry, I cannot pronounce the last name. We need to know the medical device testing standards and the guidelines related to these types of devices. Yes, I think I just already take some standards. If you want to know more standard, you can contact us. Because, for example, the PPG test, in fact, is a -2-61. IC 6601-2-61. But the standard mention about the clinical test only. For the simulator test, is not a detailed test item. So if you use our PPG module to do the SpO2 test, then we will offer a test method or test sequence to do the DUT performance and the repeatability testing. Okay. Another one is from UK, Mitrione. Okay, Mr. Mitrione. Okay, the lead hardware. I don't fully understand the lead hardware. This means the lead structure or because this for lead hardware, any structure of the hardware construction is a very complicated. If you want to ask more detail, maybe you can email our salesperson. Yeah, we can answer you individual. Okay. Okay. Next question is, can you share the PowerPoint presentation with us? Yes, of course. We will give you the website to connection to the presentation file and the webinar. Okay, and all the webinar. Okay. Okay, any question? If no question, I think we can finish the webinar here. Thanks for all you attend. And any more question, you can ask our salesperson. We will answer you individually. Okay, thank you. Thank you. Bye-bye.